We'll take a couple minutes here and talk about elastic potential energy, and this is the energy related to stretching. So this is the energy associated with stretching or compressing an object. So if an object gets stretched out or if it gets compressed in, this is the energy we're talking about. So stretching or compressing. As with all energy systems or all energies, it is a scalar. As with all energies, its units are 1 joule, which is also 1 Newton meter, which is also 1 kilogram meter squared per second squared. You don't really need to know all of these per se, but it is useful to have them in mind. Oh, sorry, that's completely wrong. I mean, it's the correct for the units, but we weren't asked for the units, we were asked for the variable. So the variable, what you'll usually see is EPE, or sometimes SPE, or sometimes US, US, U with a subscript S. This U right here is used for potential energy. Mostly when you start getting into more advanced physics, there's reasons that this ends up being useful, but just want you to be familiar with all the things you might have seen. So now, the equation for elastic potential energy is a bit strange. It's 1/2 times K, where this is the spring constant we've talked about before, times the change in the change of x squared. This is how I like to write it because it helps me remember what's going on. I think what you'll probably see on the equation sheet is just a change in x getting squared. You won't see both of these deltas. But I'll explain that in a second. This is the spring constant. And this delta x is how much stretch or compression happened. So if I take a spring that's normally 10 centimeters long and I stretch to 15, the delta x would be 5. If I take that same 10 meter spring and I compress it to 5, it also has a delta x of 5. In that case, it's actually a delta x of -5. But either way, it's not going to matter because they both get squared. And then we look for a change in how much that compression or stretch happened. It's a little weird, but once we do the examples, I think that will help. As we look at that, we can see that the constants are the 1/2 K, and the indicator is the amount of stretch or compression that happened squared. So we have an example here. A toy car is propelled by a compressed spring. How much energy is stored in the spring when it's compressed by 4 centimeters? Assume the spring constant is 250 newtons per meter. So we're going to write out our equations. So US is equal to 1/2 K. Let's put a variable on this. You can use whatever variable you want, but we'll put US on there. US is equal to 1/2 K times the change in the stretching / compressing squared, which is equal to 1/2 K times the delta x final squared minus the delta x initial squared. So in this case, we started with the spring not being compressed at all, so this will be 0, and we ended with it being compressed 4 centimeters. So delta x is equal to 4 centimeters. Now you'll notice we have newtons per meter here, so we'll have to convert that when we get to it. So we have US is equal to 1/2 K. I'm going to change that to newtons per centimeter. So that will be 25,000 newtons per centimeter. That's not going to work for us because we're going to need that meters at the end. So it'll be 250 newtons per meter. And we'll just end up squaring it's kind of messy number, but that's fine. So let's clean that up and I'll restart that. 1/2, 250 newtons per meter. Yeah. times the delta x of 0.04 meters squared, and then technically be minus 0 squared, but we won't worry about that. So that will give me 125 times 0.04 squared joules. And you can go plug this into your calculator. I'm not going to bother to do that calculation right now, but clean that up. That's what we're going to have for the change in spring potential energy. So from going from not compressed to compressed by 4 centimeters, that's the change we expect. As with all energy, we can only calculate change. Sometimes you'll see an absolute, and that's comparing to the resting natural state of the spring. So we might say there's this much energy stored in the spring at this moment. Now technically we can't say that, but what we're saying is we're implying, compared to when it was just naturally at rest, how much more energy is associated with the current arrangement. Let me know if you have questions about that, but otherwise we'll move on.